Welcome back to our discussion on states of matter. Last class or last discussion we looked at real gases. So, before that we looked at some numerical examples. And I hope that you have had the time to solve some of these numerical examples. So, we looked at, there were examples on Dalton's law of partial pressures, there was a discussion on density, there was also a discussion on how airbags work using ideal gas law, and this was the first part of the discussion. And the second thing that we did was to look at some experimental evidence for real gases. And what we will do today is to continue. So, we will discuss today some more real gases and the van der Waals equation of state. And a little bit about liquids, where we will consider vapor pressure, surface tension and viscosity. So, that will occupy us for today. Let us go back and look at our discussion on real gases. So, this is the experimental evidence, right. So, the experimental evidence comes from Thomas Andrews. And what did he do? He took a gas, in his case it was carbon dioxide, and he fixed the temperature. So, this is at a fixed temperature T. So, you take this the capillary or whatever the container in which you have your carbon dioxide gas, put it into a thermostat, and then you apply pressure on top of this, and you vary the pressure and you determine the volume, varied P and V is determined, and you do this at a number of temperatures. Okay. And for each temperature you will plot the PV graph. So, each graph, so we take a PV graph. So, we start off at a temperature which is about 50 degrees is what we said. Above 50 degrees the PV graph of carbon dioxide looks very much similar to an ideal gas behavior. The details, if you looked at, it does not follow the ideal gas behavior. P is equal to some constant over V, but it more or less looks like this. So, this is, let us imagine this was done at 50 degrees Celsius. Now, if you do it at a temperature, let us say 20 degrees Celsius, then what Andrews observed was that initially for large volumes and low pressures, the behavior looked similar to the ideal gas or the gaseous behavior, P going proportional to 1 over V. And this happened until a particular pressure when there was an abrupt change in the volume. So, this point corresponds to when gaseous carbon dioxide at that particular temperature. So, this is, we are doing this at 20 degrees Celsius, imagine. So, this is the point when liquid carbon dioxide first forms, and in this region you have liquid and gaseous carbon dioxide coexisting in your. So, this is your capillary. So, you have liquid CO2 and you have on top of this gaseous CO2, that is in this state. So, you have what is called a two phase equilibrium, liquid phase in equilibrium with the gaseous phase, and when this part is when you have both of them at equilibrium, when all the carbon dioxide gas has completely liquefied, and that is you have only pure liquid carbon dioxide, then for even a small change in volume you have to apply a lot of pressure. So, this is the liquid part, where you have purely liquid and only liquid. In this part you have only gas, and here you have gas plus liquid. So, this is also called the two phase equilibrium. Notice that at a temperature 50 degrees centigrade, you do not have all this two phase equilibrium, neither do you have the liquid line here, only gas. Each of these lines is called an isotherm, each of this. So, this is the isotherm at 50 degrees Celsius, this is the isotherm at 20 degrees Celsius, right. Now, let us look at, so and if you did this at let us say 25 degrees centigrade, let us imagine if you did this at 25 degrees centigrade, you have something very similar, and for details look at what is there in the book, you will find similar things. You have the gas line, you have the liquid gas equilibrium, and then you have a liquid phase, except that this region is smaller than this region. So, the existence, the coexistence of liquid and vapor is over a smaller region, and if you did this at various temperatures, let us now do it at 30.9 or some temperature close to 30.9, what happens is this goes up, and you can imagine. So, as I am increasing the temperature from 20 to 25, this region shortened, and at 30.9 one finds that it just goes through a point like this, right. So, this point here corresponds to this dome like this. This is at a temperature of 30.9 degrees Celsius. So, what are we saying? Above 30.9 degrees Celsius, carbon dioxide does not show liquid behavior at all. So, this is the temperature. So, the temperature above which any gas does not show liquid behavior is called the critical temperature. So, this is the critical temperature. So, this point here is called the critical temperature. And it is denoted as T sub C, for C stands for critical temperature. So, what are we saying? What we are saying is above greater than T C, no matter how much pressure you apply, you cannot, gas cannot be liquefied. Now, T C varies for different gases, different for different gases. You know that already, for example, from daily observation. Water, for example, exists as a liquid at 30.9 degrees, the same temperature at which carbon dioxide no longer exists as a liquid. So, for different gases, you are going to have different values of the temperature, and the pressure at which this happens. So, this pressure here where this happens is called P sub C, which is the critical pressure, and this volume is called the critical volume. So, now what are we saying? We are saying that for every gas there is a P C the critical pressure, Vc the critical volume, and Tc a critical temperature. Now, if you go back and look at that earlier slide that we have, you can go from this point here, call this J, to this point here K. J is gas, right. At the point J, or if you want move the J to here, this point here is J, call it. Now, this is J and it is a gas, and K is at the same pressure, this is a liquid. So, J is here, this is J and this is K, and this is happening at the same pressure, and you can go from the gas phase into the liquid phase, that is from J to K, without going through a gas liquid equilibrium. This is something that you have not encountered in real life, right. If you the best example that you could look at is water. If you looked at water over the temperatures that you and I see, you will never be able to go from gas to liquid without going through this phase, right. So, in that sense this is very different. You are able to go from the gas phase J to the liquid phase K without going through the two phase gas liquid equilibrium. So, there is a continuity, this is what was claimed. So, this is how Andrews calls it. So, there is a continuity of liquid and gaseous states. Right. So, what have we learned thus far? We have said that above Tc, no liquid phase can exist. No matter how much pressure you apply for any gas above its critical temperature, no matter how much pressure you apply, you are never going to be able to liquefy the gas. So, that is that critical temperature. And we have also learned that you can go from the gaseous to the liquid phase without going through the two phase equilibrium portion by operating at a temperature above than Tc. Then you just reduce the temperature and you can go. So, if you had a point somewhere else on the graph, you can still avoid going through the two phase equilibrium, a gaseous point. You go up above the Tc and then you decrease the temperature, and you can go from the liquid to the gaseous phase without going through the two phase equilibrium. So, that is the experimental evidence that we have. The other thing that we discussed in the last class was to look at the compressibility factor, which is defined as PV over RT. Let us look at it for 1 mole. If you want for more than 1 mole, you write it Z is equal to PV over nRT. So, this is called the compressibility factor. Now, if you plotted Z as a function of P, so I am plotting Z on the y axis against the pressure P, right. Let us imagine this is 0. Now, for an ideal gas, Z is equal to 1 at all pressures. Right, because the ideal gas equation of state says PV equals nRT. So, when we take the ratio P V over nRT, this is equal to 1 and that is independent of the pressure. So, let us mark off 1 here, and what we are saying is this is the ideal gas behavior. Now, if you plotted Z for a real gas as a function of the pressure, then you find 3 different kinds of behavior. There is one kind of behavior where Z starting off goes always positive, and examples of this are helium and hydrogen. We are doing this at a particular temperature. So, if you are doing this at room temperature, for example, this is the behavior that is demonstrated by helium and hydrogen, which means that Z is always higher than the value that you would compute with the ideal gas equation of states. The other kind of behavior that you see is that it starts off going negative or less than 1, slope is negative, and then it starts to rise. So, this is the other kind of behavior that you see in gases, and this behavior is shown by gases like nitrogen, oxygen, carbon dioxide, methane, etc. Nitrogen is a little bit, maybe we should not include that. So, primarily there are 2 types. You would also sometimes find, for example, nitrogen is a good example where Z is very close to 1 and for significant values of the pressure, and then it starts to go like that. This is observed at some particular temperatures. It is observed at some particular temperature for all gases, but if you did this at room temperature, this is more or less the behavior that is demonstrated by nitrogen. So, you have gases whose Z value is always greater than 1 for all pressures at particular temperatures, and you can also find that if you take helium and hydrogen and you decrease the temperature. So, this is at a fixed T, mind you. So, if I drop this temperature from T, so this is about room temperature. Now, if I drop the temperature to less, so you go down in temperature, what you will observe is that helium and hydrogen will also start to show the same behavior that is demonstrated by oxygen, carbon dioxide and methane, right. So, if you drop the temperature, all of them show this kind of behavior. The value of Z is less than 1 to begin with, and it drops. Well, it starts at 1 and it drops at low temperatures, at low pressures. For example, all gases behave ideally. So, this point, that is the other thing to observe. So, let me draw this here, at low pressures all gases behave ideally. Which is why Z starts at 1 for all gases. So, at very low pressures all gases behave ideally, which is why we start off here. Now, as the pressure increases, for most gases Z drops less than 1. It has a negative slope. So, del Z del P would actually be negative. It goes to 1, it reaches a minimum and then it starts to increase. Nitrogen, for example, you will find that at ambient temperatures, ambient means typically of the temperatures around in that you will find. So, at ambient temperatures the Z for nitrogen is very close to 1 for reasonable variations in pressure up to this point. So, the temperature at which, right, the temperature at which this point here or this point here where Z is equal to 1 for the different gases is called the boil temperature. and it varies for different gases. So, at that point where Z becomes equal to 1, if you plug it back into this expression, Z becomes equal to 1, we say that it behaves ideally. So, it is called the Boyle temperature, because then P will be proportional to 1 over V through the ideal gas equation of state. So, this is why it is called the Boyle temperature. So, different gases have different Boyle temperature, and you can take the same gas, and I am saying, so if I take the same gas, so this was for different gases. Now, if I take the same gas at different temperatures, and I plot Z versus P, what we are saying, this is Z equals 1 at high T, this will be at high temperatures. At low temperatures, it will show this behavior. This will be low T, with this being lower temperature than this, and this being higher temperature than this, and there is a temperature over which it is possible that you will come across where you see this kind of behavior. That is also observed. So, there are two. So, the same gas. So, I am looking at the same gas at 3 different sets of temperatures: high T, which I have represented in red, where Z is always greater than 1, low T, where it is goes less than 1 and then increases, and then some temperature over which Z is equal to 1 for a reasonable large range of pressures. So, this is the kind of behavior that one observes. So, this is the experimental observation. So, we have, what have we got? We have got the experimental evidence of Thomas Andrews, where he measured volume as he varied the pressure at various temperatures. So, these are the two kinds of things that one needs to explain, right, and the way to do it was found by van der Waals. Around 1873, for which he got the Nobel Prize in the 1900s. So, what van der Waals did was, what are the assumptions that we have when we wrote the kinetic molecular theory? There are two things that affect. So, the pressure is lower than ideal in real gases. The second that we have to address is the volume occupied by the molecules. These are the two things that we have to account for of the molecules. And the equation of state that we had is P ideal V ideal is equal to nRT. Now, what van der Waals did was to look at this very simply. So, if I have a molecule, so if I have a gas in which I have molecules, the pressure arises as a result of the collision of the molecules with the walls of the container, right. So, the pressure arises, pressure of the gas from collision with the walls. Now, under typical densities of where the gases exist, what is going to happen? If you have molecules around it, when a molecule undergoes a collision with the walls of the container, if you have molecules behind it, these things will attract the molecule. So, the gas molecules which are on the other side, that is not close to the wall, away from the wall, will pull the molecule towards it, and as a result the momentum change that you get is smaller than what that you would expect, right. So, the velocity with which the molecule would go and hit the wall of the container is decreased as a result of attraction by the molecules which are behind it. Now, it is natural to wonder why the repulsive part does not show up. The repulsion does not show up because under typical densities at which gases exist, you are never in the repulsive part. You are not at distances, the distance, intermolecular distance between molecules in the gas phase is always in the attractive portion of the intermolecular force. What am I saying? So, if I plotted V as a function of R, we know that it looks something like this, and what we are saying now is that gas phase is here. We are always only sampling the attractive portion of this well. So, always the velocity of the gas molecules that hits this thing is going to be less than if you were in this region. So, the amount that you have is now proportional to how much velocity decreases is proportional to the number density of molecules that are there in the gas phase. So, the one thing that is going to be proportional to is n over V, the number density. The number of collisions that the gas molecules have with the wall is also proportional to the density through, right, the number of collisions. So, if I have a molecule, if I have more molecules in the gas phase here, then there is more likelihood of collisions with the walls. So, both these factors, so this is the number of molecules per unit volume, and this leads to attraction as well as the number of collisions that we have with the wall, right. So, your P ideal then will become the real P modified by n over V square and some factor which is dependent upon the gas, which models the intermolecular force that you have got. So, different molecules will have different A. Okay. So, this takes care of the pressure correction. So, the pressure correction arises as a result of the attractive force existing between the molecules in the gas phase, and it varies as the square of the number density, and it is one factor which is a square of the number density and another factor which is dependent upon the kind of substance that exists. So, that takes care of the pressure correction. The other thing that we have to correct for is the volume, and that is a very straightforward correction. So, if what we have done is we have, in reality we have some things like this, although the way I have written it looks very dense. So, there are lots more empty space than there are molecules, but what we have done is we have ignored the size of the molecules themselves. We have treated them as point particles, right. We have only looked at this point particles. So, there is no volume associated with the molecules themselves. We have only volume of the gas is completely arising out of the empty space that exists. So, now we have to say that V ideal would then be V minus NB, where each molecule has a particular size. So, V ideal would be less than real volume by this factor. Now, you can plug it in. P ideal V ideal is equal to nRT, and the pressure correction is P plus n over V square into A into V minus NB is equal to nRT, and this is the van der Waals equation of state. It is very straightforward to remember this equation of state. What do we see? The pressure, so think of it as ideal pressure volume ideal is equal to nRT. How are we correcting the pressure? The ideal pressure is, if you want to get the ideal pressure, you have to take the true pressure and add a factor which is proportional to the number density times some parameter which measures the intermolecular force, and then we correct for the volume by saying that the ideal volume would be the true volume less something which characterizes the size of the molecule. So, in other words, this characterizes the size of the molecule and this characterizes the intermolecular force. Now, let us take a look at some of the numbers that we have for these parameters A and B. Right? You do not have to memorize them, but it gives you a sense of the numbers that we have got. I have A here and I have B here. A is given in bar liter square per mole and B is given in liter per mole. So, let us take nitrogen diatomic. A is 1.37 and B is 0.0387, number which does not make much sense as yet. If you looked at oxygen, it will be 1.382 and 0.0319. If you look at carbon monoxide, it is 1.472, 0.0395, and with carbon dioxide it is 3.658 and 0.0429. Right? You see the variation typically that we have observed. This characterizes the size, this is the size. Larger the molecule, as you go down, larger the molecule, larger this value of B is, and this characterizes in some sense vaguely strength of the intermolecular interaction. Continuing, here is methane 2.303 and 0.0431, ethane, just to give you a sense, what do you expect? 5.580 and 0.0651 and so on. You can look at these numbers in some book and you will find that the trend is more or less what we have explained, right. So, let us move on. Let us see what we can do with this. So, although you will not need to do this, let us rewrite this again. P plus, typically written as n square A over V square. Please, P plus n square A over V square into V minus n B equals nRT. I like to write it as P plus n over V square times A, because it reminds me that it is proportional to the square of the number density. Now, computing the pressure from the van der Waals equation of state is straightforward enough, because you just have to say is P is equal to nRT over V minus nB minus n over V square times A. So, you can compute the pressure that you will get true pressure from the van der Waals equation of state by this. But if you wanted to compute the volume given the pressure and temperature, this is going to be slightly complicated, because this is actually a cubic in V. This expression, if you expanded it, gives you a cubic equation in V. So, if you wish to compute V given P and T, then it is not going to be straightforward. So, typically you would not need, if you needed to do this, you could use a computer or some programmable calculator to determine V given that given P and T, but computing P given V and T is straightforward, and you would need to know A and B, which different for different gases, but it is tabulated. But if you plotted this cubic equation and in V, you will find that it does not match with, because this is a continuous curve. So, it is not going to match the experimental observation, but that is all something that we really do not need to worry about. So, let us move on, and I think this is enough for our discussion on gases. So, the things that we have discussed in gases, we have looked at Boyle's law, which gives you that P is proportional to 1 over V. We have looked at Gay-Lussac's law, or also called sometimes Charles' law, which gives you V is proportional to T or P is proportional to T at constant volume. Then we had Avogadro's hypothesis, which gives V is proportional to N, and we discussed the kinetic molecular model. And we introduced the ideal gas equation of state and showed how to use the ideal gas law for various computations, and finally looked at real gases. Okay, so, these are some of the things that we have looked at in gases. Let us quickly now move on to look at liquid states. Now, if you take a liquid, let us imagine that I have water and I heat it. So, heat is provided. So, put it under a Bunsen burner and you heat it, and you look at the vapor pressure. So, open to the atmosphere, looked at the vapor pressure as you change the temperature. It is a slightly complicated experiment, and if you looked at the vapor pressure as a function of temperature, so the vapor pressure as a function of temperature. So, what would happen in this particular case? If you did this experiment, there is always a vapor pressure, and that vapor pressure is something that varies as a function of temperature. This is something that you have already observed, right. So, if you watch the weather bulletin, at various every day what is said is about what is the relative humidity, and the relative humidity is a measure of how much water vapor exists in the atmosphere relative to the equilibrium saturated vapor pressure at that particular temperature, and that value increases with temperature. So, if I plotted vapor pressure as a function of temperature, it will vary something like this as an exponential dependence, and it will vary differently for different gases. So, this might be for water, for something that is more volatile it might be much more like that. So, different gases have different dependence of the vapor pressure on temperature, and the pressure, the temperature at which the vapor pressure equals the atmospheric pressure. So, when you do this, when the vapor pressure matches the pressure on top of it, that is called the normal boiling point. So, let us take this and we say this is 1 atm pressure, imagine. At 1 atm pressure, when the vapor pressure equals to 1 atmosphere, that is this particular point, this temperature is called the boiling point, the normal boiling point. Now, you must also have heard that cooking vegetables or cooking whatever things that you have, when you go up onto the mountain, is going to be more difficult, and that is a reflection of this. As you go up onto a mountain, the atmospheric pressure drops. So, you are at here some point here, for example. So, now your boiling point is lower than your boiling point at sea level, and since you need to provide the same amount of energy to cook whatever material that you have, because your boiling point is lower, you are going to have to cook for longer if you are up on the mountain. So, this is at, for example, at sea level in Delhi, which is where we are right now, and if you move up to somewhere up on the mountains, for example, on Mount Everest, then your boiling point is going to be lower for water. And so, if you are going to cook something in a cooker in boiling water, you will need to boil it for longer, because the boiling temperature is going to be smaller. So, this is how it varies, and if the pressure happens to be 1 bar, then it is called the standard boiling point, but that is not important for us here. So, what we are saying is, when, so let me just make a note of it, when vapor pressure equal to atmospheric pressure, then we have, this is called the normal boiling point. Right. So, this is the variation of the vapor pressure with temperature that you would observe. Different gases or different liquids will have this kind of behavior. Well, and the amount of energy that we need to provide for something to vaporize when you boil, for example, where you have evaporation. So, the vapor pressure, why does it arise? It arises as a result of molecules on the surface going up into the liquid phase. Again, you can explain it by the kinetic molecular model, because molecules on the surface are attracted only by the molecules which are inside. So, they have, on one side they have only gas molecules. So, this thing tends to go off quickly. So, the vapor pressure arises as a result of the molecules on the surface evaporating into the gas phase. So, there is an equilibrium between the molecules in the liquid phase and the molecules in the gas phase, and this is what leads to the vapor pressure. And when this boiling point, when the boiling point, at the boiling point, molecules in the bulk also start to go up into the gas phase, and that is where you have boiling. So, if you have this bubble formation, for example, is something that you would not observe if you did this in a closed system. Okay. So, this is something that, and this is again you could explain with regard with the simple kinetic molecular model. So, the next thing that we will look at very quickly is surface tension. Now, we all know that if you took a liquid, it tends to form spherical particles, right. It tends to form particles that are small. So, if you take a small drop, the drop actually tries to attain spherical shape of small particles, of small liquids, liquid drops, not particles. And we also know from geometry that spheres for the same volume have the smallest surface area. So, the fact that small liquid drops tend to form spherical droplets seems to suggest, and that spheres have the smallest surface area seems to suggest that there is a free surface energy. So, there is a surface energy that you have in the liquid, and when a liquid drop tries to form a spherical shape, what it is trying to do is to minimize the surface area. So, because of this free surface energy, if it goes into spherical shape, there is a minimization of the surface energy. So, if you took a drop or droplet and you expanded it, you increased the surface, then there is the energy that you have to provide to increase the surface area is called the surface energy gamma, and the energy that you will need to provide is gamma times A. So, if you have a droplet of area A, gamma times A will be the surface energy. Right? Now, the rate of the change in the surface energy when for a change in area is given by this. Right? Just by applying simple product rule, I have differentiated. So, this is the surface energy, and how does the surface energy change when I change the area of the liquid by dA? That has two terms. This is the surface energy. It will have, so this is will have Newton per meter, this is Newton per meter, and then I have a term involving how the surface energy varies with the area. But we know that for liquids, no matter what the liquid is, this thing does not change. So, this is equal to 0 for liquids, because it retains its shape, right. So, this term here is equal to 0. So, this term is equal to 0 for a liquid. Then the change in surface energy for a unit change in the area is given by this factor, which is called this surface tension. So, this term here is called the surface tension. Now, how does this thing arise? It is easy enough to understand how this thing arises if you looked at the kinetic molecular model. So, in the kinetic molecular model, we have a liquid and we have liquid here, we have a molecule here, and if you are in the bulk, you have molecules all around it, which attracts this. Now, you consider a molecule on the surface here. A surface molecule here has molecules around it, but only on one side. So, no molecules here. So, no molecules here. Well, only the gas phase. So, a molecule on the surface experiences less attractive force than the molecules in the bulk. So, the surface tension you would imagine arises as a result of this, and you can get a rough estimate of this, because if you have to evaporate, then you need this energy related to evaporation is called delta H of vaporization. So, the surface energy will be proportional, will be related to the heat of vaporization, because for every bond that you break, you can compute how much that you have. So, you will have 1/2 of this, the n over 2 will be approximately the how much the surface energy that you will need to get into the gas phase. So, this is with regard to surface tension, right. The only other, so this surface tension is a bulk property. It is a static property. Now, the other thing that we will look at is viscosity quickly. Viscosity is a flow property. So, it is a dynamic property. So, you take a tube, for example, through which you flow a liquid, which is flowing in the x direction, imagine, and imagine this is what is called laminar flow. Let us not worry about that, and you have liquid flowing in this direction. right. Each one of these arrows I can represent as an area like this, right, and I have different planes. Each of these planes has molecules which are moving in this direction, and this is the boundary, right, this is the boundary. So, when molecules in a plane move against each other, if you have to maintain constant velocity, the flow has to be constant, the force per unit area that you encounter. So, the force per unit area that you encounter, that these planes encounter, will be related to the gradient in the velocity in the direction perpendicular to the flow. So, if we are going in this direction, the gradient in the velocity perpendicular to the flow will be dV dy, and the force that you experience between the two planes, the force per unit area is going to be proportional to this gradient. So, what you are going to see is that F over A is equal to some eta times dV dy, and this thing here is called the viscosity. And how does one understand this in a molecular framework? You have two different planes and the molecules are moving, and think of it that think of one plane as one train in which you have molecules that are moving with higher velocity, and another train which is moving at a slightly slower speed, and a molecule is jumping from one train to another train. So, if this is moving with larger velocity and it jumps into here, this thing tends to catch up, whereas when this thing moves, when a molecule from here goes down to this phase, then this is moving slower. So, this gets slowed down, right. This is how one understands what is it happening in the molecular model. So, this relation which relates the force per unit area to have this constant flow is something that we call, through this gradient, is called this viscosity, and this has units of poise. Okay. I do not think we need to discuss much more than this. So, this gives you a molecular understanding of how viscosity arises, and it is also related to intermolecular forces, as you might have already guessed. So, this is what we will close our discussion with on states of matter. So, things that we have discussed are intermolecular forces, gases, and a very quick run through of liquids and their properties, primarily vapor pressure, surface tension, and viscosity. So, with that we will conclude. Thank you very much.